So we are Edgeless Systems. This is our first webinar. Let's dive right in. So we are a German company. We have roughly 10 employees. Our focus is on building open source confidential computing software. We were founded in 2019, and we are funded through research grants and venture capital mostly at this point. A few words about myself. So I did a bachelor and a master in computer security, worked as a consultant for some time after that, then quit that job to do a PhD in system security. And while doing that PhD, I discovered this new interesting field of confidential computing, and I worked with Microsoft researchers during my PhD, and after my PhD in 2015, I joined Microsoft to work full-time on confidential computing, and our group sort of, I think we can say that we started the foundation of Azure confidential computing. And in 2019, finally, I quit my job at Microsoft, and I called a few friends from uni, and we started this company called Edgeless Systems here in Bochum, Germany. Right, so agenda for today is, what is confidential computing? Second, what are the applications and use cases? Third, what does Edgeless Systems do precisely? And fourth, how do I build and deploy confidential apps? First three are rather high level, and the fourth part is very much focused on developers and engineers. So what is confidential computing? First some motivation. So clearly we still have some trust crisis in computing, right? It's 2021, but things are not as they should be. So because of a lack in security technologies, companies still don't take full advantage of the cloud. Companies are not trusted with data by legislators and customers, and companies don't monetize or share sensitive data as they should. Bottom line is, companies waste money and leave huge potential values untapped. So why do existing approaches fail? Of course, we could talk about this all day, but a very high level observation is that we have, in some ways, we already have good technology. And of course, we have encryption at rest, so you can encrypt your data while it's stored on disk, of course. We have encryption in transit. So of course you can encrypt your data securely when you're sending it over, for example, to your cloud provider. However, what we don't have is we don't have encryption at runtime. So once you've sent your data over to your cloud provider, and the cloud provider is supposed to do anything with it, it needs to decrypt your data, and then it will be in plain text, in RAM, and possibly also in disk, and you don't know what's going on. That's one key problem that we have. And the second key problem that we have is that with current technologies and approaches, we don't have verifiability. So once you've sent your data over, you have no idea which apps are running there, who's maintaining the infrastructure, what the infrastructure looks like, and so on. And that's another key deficit of current solutions and current technology. Here, bottom line is, hackers and viruses can access your data when it's being processed, maybe also malicious insiders, and it's impossible to tell what's going on. So in comes confidential computing, and we see this as a game changer. So confidential computing is a hardware-based technology that allows you to run sensitive workloads in so-called enclaves. And these enclaves can be created on commodity Intel and upcoming AMD processors. So you as a programmer, you can tell your processor on-prem, local, on your desk, or in the cloud to create a secure enclave on an otherwise untrusted system. And these enclaves, they have three defining properties. So the first one is, enclaves are strongly isolated from the rest of the system. So no other system component, other than the processor can look inside an enclave. Not the hypervisor, not the operating system, not some malware running on the system. And also not any other hardware. The second important feature is that everything that happens inside an enclave, all code and data lying around in an enclave, are encrypted even at runtime. So no code or data from an enclave ever touches the main memory in plain text. And the third great feature is enclaves are verifiable remotely. So you can get a certificate from your confidential computing processor that it ran a certain piece of code on a certain piece of data and produced certain output. And you can infer from this certificate that this is a real CPU process provided by Intel or AMD, and you can make sure that it's doing precisely what you want to do. And now with this technology, we can finally close the gap that we saw on the previous slide, namely that we don't have encryption at runtime and that we don't have verifiability. Yeah, the paper you're seeing down here is something that I wrote with my colleagues at Microsoft Research back in 2015. And some people believe that this paper coined the confidential computing term. And this was one of the first papers or first works to design an end-to-end secure system for the cloud using this new technology. And in the Intel world, it is called SGX. And in the AMD world, this is called SEB. And maybe a fun fact, Intel initially wanted this to be a technology to enforce copyright. So wanted to prevent people from burning DVDs or copying games. And when we read about this at Microsoft, it was clear to us immediately that this was not, well, it was great for copyright, of course, but it was really could provide more value in the context of the cloud and general data processing. Right. So if this was a bit too technical for you, here's an abstract view of what this new hardware and these enclaves can do for you. So you can think of a super secure black box that no one can look inside. And let's see, you can imagine that you have secure channels to this black box, and you can give this black box some data, some code, and it will run your code on your data, and it will securely give you the results back, and you will get proof that this black box is actually genuine and that it ran precisely your code on your data, and that no one could access that data or modify it while it was being processed. And yeah, in case you're asking yourself, okay, that's great, but you're saying you need new trusted hardware. Where do I get this hardware? So the answer is the hardware is surprisingly prevalent. So it's almost a commodity. So if you have a recent Intel laptop with a Core i5 or Core i7 CPU, then chances are quite high that you have the features the hardware features to create an enclave. If you're looking at the cloud providers, Microsoft, Google, especially, then it's very easy to create a secure enclave in their clouds. They have the processors already. Okay, so let's compare this to existing trusted hardware. So we say that from our perspective, there are 4 defining features with regard to trusted hardware. First feature is you can run high-performance general purpose code. Second feature is you can use the hardware to protect encryption keys. Third feature is you can have verifiability through remote attestation. And the fourth feature is runtime encryption, what I mentioned before. Now, if you look at existing or maybe more well-known technologies, we have smart cards, for instance, and HSMs, hardware security modules. So people use smart cards and HSMs to store their cryptographic keys on-prem or in the cloud. And this is what this hardware is supposed to do. Next, we have TPM. So if you're using trusted boot on your laptop, like BitLocker, for example, then this is almost certainly based on TPMs. TPMs are special purpose trusted hardware, and they are a bit like smart cards and HSMs, but they also have remote attestation features. Next, what you may have heard already is untrusted. Untrusted is a technology that is primarily used in the mobile sector, and it allows you to run general purpose code in an isolated way. Now, with the new hardware from Intel and AMD, we get all the 4 features combined, and this is what makes up confidential computing. So you have general purpose code, sealing of data and keys, you have remote attestation, and you have runtime encryption. And these, from our perspective, this is what defines confidential computing. So everyone is excited, not only us. There is, for example, the Confidential Computing Consortium, which was formed last year. Most of the big American and Chinese hyperscalers and tech players are in there. We also joined last year. And most of these folks are now trying out different things. So the hardware is there. There's some software, and now everyone is trying out different things, and everyone is quite excited. And it's exciting times for the field. Good sign is, for example, that Forbes, the famous magazine, had confidential computing on its top 10 list of digital transformation trends for this year, next to heavy hitters like 5G. And we see this as a great sign that the tech will finally go mainstream and make your application, our applications way more secure than they were before. So current state in the cloud is as follows. We mostly see infrastructure as a service offerings from the big cloud vendors. So if you're looking at Azure, you can just with a few clicks get a VM that has a possibility to launch enclaves. And yeah, that's it. But you need to bring your own software essentially. It's similar at IBM. They have some bare metal machines and some frameworks. And recently, Google also started to offer a rather basic but very prominently advertised confidential computing service. So if you go to GCP, the Google Cloud Platform, and if you create a new VM, you now have this new checkbox down here, confidential VM service. And all you need to do is to click that checkbox, and you will get a VM that's running inside an enclave. However, it's pretty bare, so you don't get any remote attestation features here, and they're also using an older version of AMD SED, so it's not so super secure. But we see this as a great sign that Google is now dedicating this very expensive screen real estate to this confidential computing feature. Yeah, bottom line is hardware is there, you need to bring your own software. And this is where we are trying to help. So let's look for a second at competing technologies. So you may have heard of homomorphic encryption. Maybe you've heard of federated learning. You've certainly heard of blockchain and smart contracts, and maybe you even have played around with those. Our perspective on this is all 3 technologies are great, and I mean, especially homomorphic encryption is almost like the holy grail of computer security, if you will. However, what we see is that these technologies are either very expensive and difficult to apply in practice, and that they have different drawbacks. So if you're looking at homomorphic encryption, and homomorphic encryption is the approach of processing on encrypted data using math and crypto. Super exciting, but it's also super expensive, and you don't have normally verifiability and integrity or correctness. If you're looking at federated learning, and this is an approach where you want to jointly train AI, then, well, you still have folks training on plain text AI, and you don't have end-to-end security. Now, if you're looking at blockchain, and there are some connections between blockchain and confidential computing, but so people use smart contracts to share and jointly process data in a verifiable way. So there's this verifiability aspect. However, you typically don't have confidentiality in smart contracts, and it's also oftentimes rather expensive and low throughput. So our perspective here is, if you're trying to apply one of these technologies in practice, chances are quite high that confidential computing is actually the more practical, more secure solution. Okay, let's take a look at applications and use cases. So, from a high-level point of view, we think that there are two main benefits that confidential computing can bring. First one is increased security for existing apps. So let's say you have an existing app running in the cloud and you want to make it more secure, or you have an existing app running on-prem and you want to shift it to the cloud, but you're not trusting the cloud provider, or maybe you're being held back by regulation. What you can do is you can shift your application to a CC stack, and you will get increased security. You will get great protection against traditional breaches, because external attackers and malicious insiders, it's not enough for them to breach your system now. They need to breach your system, and then they need to breach inside your enclaves, and this is very difficult, and sometimes even impossible outside of a lab environment. And of course, yeah, you can use the cloud with confidence now, and you can potentially save a lot. This is the first benefit. The other big benefit that we're seeing is that confidential computing opens up completely new possibilities, completely new applications, and new data-driven business opportunities. So first is, using CC, you can design applications where you can lock yourself out of your data in order to meet privacy expectations and be compliant. So you can analyze your data without looking at it. And this is quite exciting. And we're working on a big project with a German retailer in this context. So they can collect the customer's data, they can process it, and they can prove to anyone, their customers, their partners, and their regulators, that they cannot see the raw data and that they're only getting aggregated results in the end. And that's quite exciting. And the last point is, you can now use this as a trusted third party, maybe in a sense of a smart contract, to design interesting applications where you can share data with your peers or your customers without actually sharing the data, right? So you don't need to show your data to your partners or to anyone, but you can still jointly process that data, or you can sell access to your data to someone who wants to train an AI model on it, but you don't need to actually give the data to that person. And that's super exciting. So here are a few examples that we are exploring with our early partners. In manufacturing, what we see is folks are quite excited about pooling industrial telemetry data in order to train AI for predictive maintenance, for example, without having to reveal trade secrets. In mobility in smart cities, there's similar use cases. So, for example, all the car makers now want to become like Tesla and train their own self-driving AI. However, some of them are reluctant to actually collect all the data, and maybe, especially in Europe, these car makers are not allowed to collect all that data. So CC can now open up the possibility to collect this data in a responsible and verifiable way, and help these companies to get an edge in their business. Finance is also super interesting, and there are quite a few use cases in finance. So, for example, banks are interested in comparing different forms of financial data for fraud detection or money laundering, but they're typically not allowed to show that data to each other, and they don't want to show it to each other. That's quite exciting, and of course, healthcare is also very exciting. And actually, quite a few, well, the biggest CC applications out there are in healthcare at this point. And as far as I know, the biggest worldwide is in Germany, and it's called the e-Rezept. This is German for e-prescription. And so what happened there last year is the German government wanted to have a nationwide digital service for prescriptions, end to end, from the doctor to the pharmacist to the patient. And of course, there's lots of data flying around, and now the reference architecture for the e-prescription, the e-Rezept, it requires that the whole stack is being built on CC, so that it is end-to-end verifiable and end-to-end secure. And yeah, it's a super exciting project, and we actually help with the reference design. And now this is being built by IBM, and it's going to be the biggest CC application in the world, as far as I know. And yeah, I at least well-informed people tell me that it's going to be the biggest, with thousands of servers, and it's going to be very exciting. Okay, let me check for questions. Okay, looks like we are good on the questions side. But let's take a look at what we are doing at Edgeless Systems. In one sentence, we make CC easy to use, scale, and integrate. And I could add for free here, because our focus is actually on, or almost for free. Our focus is on free open source. So at this point, we have 3 projects. We have a project called Ego, and this is already sort of on GitHub, but we will have a proper release in the next 1 or 2 weeks. And this is the easiest way to develop applications for CC in a modern and cloud-native way, using the famous Go programming language. The next thing that we have is called Marble Run, and Marble Run is already fully open source, and it is a DevOps tool that allows you to scale confidential apps on-prem or in the cloud on a normal Kubernetes cluster that has the right hardware. And if you deploy your apps using Marble Run, you get great additional features like end-to-end verifiability, and more. And I talk about that in a bit. And finally, we have our Edgeless DB, and this is a SQL database that is running entirely inside a secure enclave, and has some great features. Like you can have a smart contract that dictates what the database can do and what it cannot do. And we are using this in the project with the retailer that I briefly described. And Edgeless DB will be open source in Q2 this year, and currently it's in private preview. We're also doing some things on the software as a service side, but that is TBA. Okay, Now it's getting a bit more tech heavy. We're starting to get into the engineering and DevOps territory. How to program and deploy apps. So let's take a look at the software hardware stack again. Of course, if we have no confidential computing, we need to, like we have almost everywhere today, you need to trust the whole software hardware stack. So you need to trust your own app, you need to trust the library it uses, operating system, hypervisor, hardware, and so on. Now there are three flavors of confidential computing, how you can now cut this attack surface and put your secrets inside an enclave. The first one is confidential functions. And this is what people started doing initially. And this is what Intel SGX was initially designed for. So typically you use the Intel SDK, you use Microsoft's Open Enclave, you use the Rust SGX SDK. These are like low-level SDKs. And what you do is you split your app into a trusted part and untrusted part. And the trusted part could be the part that deals with passwords or with credit card numbers or social security numbers. And then you design a protocol between your app and the trusted part, and you only have the trusted part run inside an enclave. And that can be a great design, but it can require quite some engineering and thought on the engineering side. Now, the next thing, and this is what we are focusing on, is putting entire apps or entire containers inside enclaves. And essentially what you do is you don't split your app, you just take your entire app and put it inside this enclave. This can make things quite a bit easier, and with our Ego you can actually take almost any existing Go application, like HashiCorp Vault or many of the cloud native apps, and just run them inside an enclave, and it will just work. So that's great. Makes things a lot easier, and well, makes things easier, but still leaves most of the stack outside of your trusted computing base. So we see this as a great trade-off. Another thing that is now on the horizon are confidential VMs. So as I was saying earlier, it's already possible to have sort of confidential VMs in Google. Now AMD is going to release new CPUs Q1 or Q2 this year, and they will have really confidential VMs. These confidential VMs will have good memory encryption. They will have actual remote attestation capabilities, and with these features, you can just lift and shift entire VMs. This, of course, makes it maybe even easier to deploy your apps. The problem is you're now moving your whole operating system inside your enclave. Maybe you don't want that. Intel will also have some CPUs that will be capable of this, but they probably won't arrive. Not sure. There's no release date yet, as far as I'm aware. We plan to support these confidential VMs as well with our Marble Run. And our vision is make it as easy as possible to have confidential VMs or confidential apps, confidential containers, and use Marble Run to deploy and manage these. All right, I think there's a question. Edgeless DB runs its whole code base in an enclave. How are you able to defend against sidechain attacks present at SGX? That is a great question. So you may be aware that, well, there is no such thing as 100% security. So it is possible for the operating system to use different means to listen on, or to spy on the enclave. So the enclave can, for example, the operating system can unmap the memory that the enclave is using, and then can observe how the enclave is accessing memory later on with some granularity. And there are different side channels of this kind. our perspective on this is many of these side channel attacks only work in lab environments, and we are also building countermeasures against some of these side channels into our apps. Yeah, of course, as I was saying, there is no such thing as perfect security. So if a state actor is able to access your enclave physically, like takes a CPU, put it in a lab, and run tests on it, at one point they will certainly be able to break into your enclave. However, this is like light years ahead of what is the case now. At present, the aggressor just needs to walk to the data center and steal your data at runtime. Maybe they can just hack into your hypervisor operating system from the outside and steal your data. So bottom line, side channels are a concern, but we are quite positive here, and we have some good countermeasures. So this is a sort of a confusing slide, maybe on first glance. But what we try to do here is we try to map the open source landscape. And what is interesting here is that the open source landscape grew from the top and the bottom. So top here we see the foundations, and these are the low-level SDKs that people initially wrote in order to be able to program the hardware. And I worked on the Open Enclave SDK at Microsoft. But these SDK are quite rough and hard to use. You can essentially only program them in C. Now, the next thing that happened was language runtimes were built. Google built the C++ SDK, Baidu built Rust SDK, Fortanix built Rust SDK, and we are now releasing our Go SDK. And at the meantime, also library assets came up, and these are trying to create Linux-like environments inside enclaves, and for different reasons. And now the latest development is that we're now seeing the first DevOps tools. So there's a containerization tool from Alibaba, and there's Marvel from our side. Yeah, and then we have a couple of app frameworks, and they came also up quite early. I used to work at CCF at Microsoft. There's some blockchain connection with that, and probably the only most famous app out there in the open source space is from the Signal messenger. So Signal is using SGX to securely store contacts of its users, the address book, and they are doing this using the SGX SDK in a confidential function way. There's another question. I assume you issue native calls to your Open Enclave SDK from the Ego framework. Okay, let me read the question. I assume you issue native calls to the Open Enclave SDK from an Ego framework. What do you do to protect those native calls? So we're running on Open Enclave, and the good thing about running on Open Enclave is that Open Enclave is not tied to Intel. It can also run on ARM and potentially on AMD in the future, not sure. We're running on Open Enclave, and everything is running inside the enclave. So there are no insecure connections between Ego and the Open Enclave. It's all inside the enclave. I hope that answers the question. So in case you're interested in the open source space, many of these projects will present their work at our OC3 conference that's happening on March 11th in the afternoon, European time. So it will be morning in the US and unfortunately night in Asia. But yeah, we will have talks from Baidu, from Alibaba, from Microsoft, from Intel, from ARM, and of course also from our side. Okay, let's take a look at our open source ecosystem and how you can actually use it to build something. Now it's really getting into the engineering territory. As I was saying, so Ego can be used to port and run almost any Go application inside an enclave, and has some great integration with Visual Studio. And let me just demo this to you. One second. So yeah, that looks good, yeah. So I am connecting to a local VM that has SGX features. And here's a simple hello world. It says hi from Enclave. It's written in Go. And what I now normally would do is I would type go run main.go, and it would just compile, and this just compiles and runs this application, and it prints hi from Enclave. Of course, in this case, this is a lie, right? So it's not running inside an Enclave. Now, if I want to run this site inside an Enclave, all I have to do is type ego go build main.go, and it builds it. Next thing that I do is I type ego sign main, because if you want to run something in an Enclave, it needs to be signed. And last thing is ego run main, and this is now running this inside an Enclave, and it will print out hi from Enclave. Yeah, and this is how easy it is to develop applications for the Enclave using our Ego project. And instead of the simple hello world, you could just compile and run HashiCorp Vault, for example. And let me just copy something over here. Right, so, and if you want to, and if you now, for example, wanted to have remote attestation with a remote party, all you need to do is import our Enclave library, and then you can, for example, hash some. Let's write this into a message variable. Message, print the message, and then we could hash the message and ask the CPU to give us a report. So in Intel and Open Enclave speak, a report is the remote is a certificate that you get from the CPU that you're running on an actual Intel SGX CPU inside an Enclave. And if you now wanted to use this feature from your Go code, all you need to do is use our library to get a certificate for this hash, and then you could use this and pass this on to a third party and convince the third party that you're running a certain code, that you produce this output, like we had in this black box example. As easy as that. So that's the first step. Second step is you have your app, now you want to deploy it in the cloud and scale it in Kubernetes, and this is where Marble Run comes into play. And now let's take a closer look at what Marble Run does. So Marble Run, we like to call it the service mesh for confidential computing. And in case you're not sure what a service mesh is, or you haven't heard about a service mesh before, here's what it is. So imagine you have a scalable web application in the microservice sense, and you're running this on Kubernetes. Then maybe your application would look like this. You have a web front end with a couple of instances. You have some app logic with 2 instances, and you have some state which is kept in 4 different nodes. If now someone visits your scalable web app, Kubernetes takes care of directing this request to one of the front end pods, and then the front end pod will ask the app for an app logic instance, and Kubernetes will take care of connecting the front end to an app logic node, and then also connect one of the state nodes. So, and if you now figure, okay, we are getting so many users, we need more web front end nodes, or we're getting so much data, we need more state nodes, you can just tell Kubernetes to scale things up. And this is what Kubernetes is all about. Now, service mesh. So in most contemporary deployments, people use a service mesh in conjunction with Kubernetes. And the service mesh takes care of, it's part of the infrastructure, and it takes care of some extra stuff. So service meshes inject proxies into your pods that are running on your Kubernetes cluster, and these proxy intercept the traffic. And what they do is they do then three things. They take care of encrypting the traffic between the pods. They give you observability of the traffic, and they can do some magic with regard to load balancing and traffic rerouting. Yeah, this is why most people use service meshes these days. And service meshes take care of a lot of boilerplate stuff that you don't want to implement every time you're creating an app. Now we see, so Marble Run is another extension. So Marble Run is now an extension for these, or runs besides these normal service meshes, and Marble Run adds features that are important for confidential computing. And it tackles a range of questions and challenges. So when we started this project, we oftentimes ran into the following questions. So if we have nodes, individual nodes that are running on secure enclaves, that are running in secure enclaves, that's great. But how do we test the whole cluster of secure enclaves? How do we know it's the right number of enclaves? How do we know it's the right type of enclaves? How do the pods and the enclave test each other? How do we terminate secure connections not inside the proxies but inside the enclaves? How do we manage secrets between these pods? What happens if a pod is moved from one physical node to another physical node and its keys change? And how do we update code? And how do we do this with minimal changes and minimal effort on the developer side? Yeah, this is why we created Marble Run, and Marble Run takes care of all of the things and some more things. And here's what the flow looks like from a DevOps perspective. So first step is you build and you containerize your application as you normally would. So go build your service, and then you package that into a container. Okay, done. Only in this case, use Ego. All right. Next step is you define your Kubernetes cluster as you normally would. So my cluster.yaml, this is something that you will always define. So you tell Kubernetes, okay, I want to have these containers running there and these containers running there, and they should have these parameters. Now, what is new in our case with Marble Run is you also define what we call a manifest. And this manifest contains some CC and enclave specific definitions, and it defines how the cluster should look like from a CC perspective. And then step 2 is, as normal, you just use your normal tooling to install the cluster, maybe in the cloud, maybe on-prem. And yeah, that's super easy. And now here's what happens next. So once you have installed everything, you have this cluster, and there are your services. Your services are running inside this cluster, maybe service A and service B. And in the case of Marble Run, there's also what we call a coordinator that's running inside your cluster. And now the next step is once everything is set up, you call into the coordinator enclave. So these are all enclaves now. And you use an REST API to set the manifest. And then the coordinator knows what type of parameters it should enforce inside the cluster. Next step is all the services inside the cluster, they automatically call the coordinator. There's nothing you need to do. This will happen automatically. They will tell the coordinator, okay, hey, I'm you, I need my parameters. The coordinator will use the verifiability features of Intel SGX enclaves to verify that this service complies with the manifest, and will then hand over secrets and parameters in the form of files or environment variables securely to the services. And then these services they know who the other guys are, and they can securely, end-to-end securely, talk to each other, enclave to enclave. Now, step 4, and this is also something new, the user of the application now should verify that the cluster is in a certain state, and they can call the verify function, it's again a REST function, on the coordinator, and they will get back proof that everything is running inside enclaves and that the whole cluster adheres to the given manifest that was installed in step 3. And I'll show you an example of a manifest in 2 minutes. And step 5 is as normal, you can now use the app. Benefits here are, the admin and the DevOps engineer, they can use the existing tooling. They can scale everything as normal, they can update code, they don't need to change much, and they don't need to worry about machine-specific secrets and hardware details. The user, they know that everything runs inside the enclave. They know that everything is always encrypted. They can, if they want, get the precise proof that the topology of the cluster has a certain form, and they know the identity of the cluster, and they know who can recover the cluster in case of a disaster. These are great benefits, and you can't achieve that with current technologies and current software. And now here's a demo. Let's see. I created a cluster in Azure earlier for a typical DevOps demo app that is rather famous, and it has a topology similar to what we discussed before. So there are some web nodes, there are some emoji, there are some application logic nodes. In this case, this is about emoji voting, and then there are some vote nodes which track the individual votes. And I created a cluster in Azure. I told Azure, okay, I want to have a Kubernetes cluster, and this should run on SGX-enabled hardware. And now this app is running at this URL. Let me post this into the chat. And you can open up this URL, and let me do this as well. And what you will get is a certificate warning. And please click that away. That is intended because this thing uses a special certificate issued by the coordinator. What you would need to do now is you would need to go and verify that the coordinator is in a good shape. But please skip this for now. But if you go to this web application, this is all now running scalable, end-to-end secure inside enclave. So your browser is directly connected into an enclave. And this app, it's a Go-based app, is running in an enclave, and you can securely vote for your favorite emoji. And as you're seeing, there are already quite some votes. The reason why there are quite some votes is that we have a bot running that is doing some voting to make this more interesting. And we have Linkerd running here. Let me log into my VM here. Something that I wanted to show you. So we have Linkerd running on the cluster as well. So Linkerd is a service mesh, and it allows to observe the cluster in a quite nice way. And what we see is we have one emoji voting instance, one emoji instance, one voting instance, one web instance, and we have one vote bot who's doing all the voting. Now, what we can do is we can, despite everything running inside enclaves and everything having secure connections, we can still use normal tooling like Grafana to observe what the cluster is doing, but we just can't see any raw data. So we will get some nice images with regard to traffic. Yeah, not too much traffic going on at this point. And now comes the cool part. What I can now do is I can now go back to my cluster here, and I can start scaling things up despite everything running inside enclaves. Right, scale. So I can now, for example, scale the web front end to 3 replicas. And it will just do it. And the coordinator will take care that everything is still compliant with the manifest. And we can now see in Linkerd that it's actually creating new instances of the web front end. And yeah, so we can use our existing tooling. We can really scale things up and down, but it's verifiable, end-to-end secure. And we think that is a great feat. Yep. So in the interest of time, we started a bit late. I'll try to finish on time. Let me just show you a brief view of a sample manifest. So everything is on GitHub. This is what the manifest of the emoji voter application looks like. So it's quite short. It's not scary at all. You essentially define your enclaves, and you can get these values easily from Ego. So there's a function called Ego dump info, and you will get the info for your enclaves. And you can specify which issuers you trust. You can specify certain hashes of enclaves that you trust. And you just define what enclaves you are willing to have in your cluster. And then you define the parameters for your enclaves. You define how many of them you can, well, you can limit the number of enclaves. And you can also inject secrets. And this is where things get interesting, but it's probably too deep for this talk. And if you're interested in secret injection and secrets management, I suggest you look at the manual, or you just drop me a mail and we can discuss this. Right. So changes that we need to make in the existing emoji voter code base were minimal. Essentially, we are just using our library to get the TLS secrets, and then use TLS throughout for gRPC and for external connections. Yep, and we're trying to reduce this to 0 changes, to move this into the runtime itself, so that you can just in the future just lift and shift and don't even need to worry about adding these 10 lines of code. Conclusion. Thank you all for staying with us this hour. Here are the main takeaways. So CC makes systems end-to-end secure and verifiable. It can prevent breaches. It really can raise the bar by quite a bit. It allows you to use the cloud with confidence, and it allows you to create new data-driven business models. However, CC requires some thought and engineering if you want to apply it in practice, and we are trying to make it as easy and seamless as possible. We are an early stage company. We are very much interested in learning about your use cases. We are very much interested in interacting with you. So we are very happy about any pull request issues or stars on GitHub. And if you think that there's an interesting project at your company that could be solved using our tools, please don't hesitate to get in touch. And we are quite interested in engaging in pilot projects at this point. Yeah, thank you very much. My email address is fs@edgeless.systems. And let me check if there are any more questions. One second. No, so yeah, thanks. And please get in touch and see you soon. Goodbye.